Okay, the math professor is on the air once more. Return with us now to that subject we all love, statistics. Since I'm here by myself, I'm taking off my mask. Okay, so we talked about confidence intervals, both two-sided and one-sided, in our previous classes. Now we're going to talk about a large sample confidence interval for mu. When n is large, the quantity x bar minus mu divided by the quantity sample standard deviation divided by the square root of n has an approximate standard normal distribution. This goes along with what we talked about with the central limit theory. If you have enough numbers, starts to look like a standard normal. Consequently, x bar minus z alpha divided by 2 times sample standard deviation divided by square root of n is less than or equal to mu, less than or equal to x bar plus z alpha divided by 2 times sample standard deviation divided by the square root of n. So this is a large sample confidence interval for mu with confidence level of approximately 100 times the quantity 1 minus alpha percent. All right, so you can see it's very similar to what we have already covered during our study in chapter 8. All right, then they give us this example, 8-5 of mercury contamination. A sample of fish was selected from 53 Florida lakes, and mercury concentration in the muscle tissue was measured in parts per million. The mercury concentration values were, well, forget it. I'm not reading you the mercury concentration values. They want us to find an approximate 95% confidence interval on mu. All right. Although I think saying an approximate 95% confidence interval is redundant. When you find a confidence interval, that's already an approximation. But I digress. All right, so our example continues. Summary statistics for the data are as follows. Our variable is concentration of mercury. Our sample size is 53. The mean in parts per million is 0.5250. The median is 0.4900. Our standard deviation is 0.3486. Our minimum value is 0.0400. Our maximum value is 1.3300. Our first quartile is at 0.2300. Our third quartile is at 0.7900. Why is it not listing the second quartile? Because the second quartile is the same as the median. But I digress again. Now, because n is larger than 40, The assumption of normality says it's not necessary to use, but we use that assumption. The values that we need, n equals 53, x bar equals 0.5250, our sample standard deviation is 0.3486, and z of 0.025 equals 1.96. All right? Now, I'm going to count on you guys to start figuring out what the z number is without my doing the whole calculation that confidence interval percentage equals 100 times the quantity 1 minus alpha percent. All right, so the approximate 95% confidence interval on mu is x bar minus z of 0.025 times sample standard deviation divided by the square root of n is less than or equal to mu, less than or equal to x bar plus z of 0.025 times sample standard deviation divided by square root of n. We plug in our numbers and bloody hell, I'm not sure you want me reading those off to you. And we come up with 0.4311 less than or equal to mu, less than or equal to 0.6189. All right. Because of the large variability in our mercury contamination concentration measurements, our interval is pretty wide. But good enough to be going along with. All right, so for a large sample size, our approximate confidence interval for any measurement, suppose that theta is a parameter of a probability distribution, and let theta hat be an estimator of theta. Then a large sample approximate confidence interval for theta is given by theta hat minus z alpha divided by 2 times the standard deviation with reference to theta hat, less than or equal to theta, less than or equal to theta hat, plus z alpha divided by 2 times the standard deviation with reference to theta hat. All right, so okay, we're not going to do the t distribution today. I'll save that up as a nasty surprise for tomorrow. No, I'm kidding. T distribution takes a little getting used to, but it's not hard. All right, so what do we do? Right, obviously this is the general expression for a confidence interval, right? In this case, a large sample, approximate confidence interval. But what do we do if we want a one-sided equation? We take whatever side we want. For example, we might want theta hat minus z alpha, right? Because it's one-sided, we make it z alpha. times our standard deviation with reference to theta hat is less than or equal to theta. Same thing if we want the upper bound confidence interval. We would say theta is less than or equal to theta hat plus z alpha times our standard deviation with reference to theta hat. All right, so that's going to be it for the slideshow today. 4 slides, no waiting. Now, what are we going to do to entertain you for another, must be an hour? We're going to work some problems. All right, so I'm looking at these problems and I'm saying, who has more than 40 sample size? Okay, so that looks like it's this one, and this one. All right, so let's take the first of these. Copy. Let's go here. We will paste that in here. Now, of course, we have no idea in the universe what all these numbers are, right? They could be midsummer measurements in different cities of the temperature. They could be the number of jackrabbits counted in passing during different periods. Who knows? But it doesn't matter. All right, so we're going to look and we're going to insert our equation. And our equation, we start with x bar go backspace. All right, there we go. Minus z I can hardly wait till they figure out how to make this stuff just right at your fingertips. All right, alpha divided by 2 oh, damn it. And we want the fraction, not exactly where I wanted it though, guys. All right, there we go. Up here we want sample standard deviation. Down here we want square root of n. Okay, and because I am so lazy, I am going to just copy that. All right. We want the mathematical symbol for less than or equal. Back to math. All right, there we go. Less than or equal. and go to the other side, and again we say less than or equal, and then I put in what I copied before and just change the minus symbol to plus. Okay, there you go. Now, what do I need? Well, I need what is n, so we can get square root of n. What is x bar, and what is our sample standard deviation. All right, well, easy enough. So, our x bar equals the average, although usually we don't spell average with a W. All right, there you go. I highlight all my numbers. All right. Close parenthesis. All right, so 88.7805 is our x bar. We want to find our sample standard deviation equals STD EV dot S, and again I just highlight all my numbers. And now, what else do I need? I need n equals, and I'm going to go equals count, left parenthesis, highlight my numbers once more, even though I'm pretty sure I already know what this is going to be. All right, so it gives me that we have 41 numbers. Now, let me move this over a little bit. Right? Yeah, there we go. So, now that I have all of these, what level do we want to do this at? I suggest, first of all, we start with a 95% confidence interval. Or if you listen to the book, approximate confidence level. All right, so I'm going to say equals, right? I'm going to do the left side of the equation here, equals my x bar minus 1.96, for 95%, that is z alpha divided by 2, times my sample standard deviation divided by the square root, SQRT, left parenthesis, 41. All right, so that gives me my lower bound, which is 83.885, right? Less than or equal to mu, less than or equal to. Now I'm going to calculate my upper side equals x bar plus z alpha divided by 2, 1.95, times my sample standard deviation divided by the square root, SQRT, left parenthesis, click on 41, right parenthesis. All right, so our approximate 95% confidence interval is 83.885 less than or equal to mu, less than or equal to 93.676. Now I am tempted, actually, because of significant figures, to knock off these things after the all right, bloody hell. One more interruption and we promise we'll stop.